So once again, you are welcome. We are almost getting to the end of productivity section. We are getting to almost the end. We first of all looked at the technical Malmquist productivity index. Then, using a new data set, we demonstrated the cost productivity and compared it with the technical. Now, we are going to introduce another productivity, which is also technical productivity, but then it is called Biennial Malmquist productivity. Okay. Technical Biennial Malmquist productivity. Now, the previous one is technical Malmquist productivity. So you're going to compare the Biennial Malmquist Index with the Malmquist Index, Malmquist Productivity Index. So let's begin. Now, first thing you want to notice that there are different measures of productivity, different ways. There's adjacent one, the base period, the sequential, the meta-Malmquist. The meta-Malmquist is an interesting one. It's where you blend the meta frontiers together with the Malmquist Index. And you get that also in the max DEA, which is hinged more on O and Lee. We have the global Malmquist by Pastor and Lovell. So there are so many Malmquists. And then we have the global Malmquist Leuenberger by O. Okay. Remember, you can see that O and Lee wrote 2010. O alone wrote 2010. That's the Malmquist Leuenberger. And then you have the global cost Malmquist. That is by Tuhidi et al. Global cost Malmquist. Now you already know the cost Malmquist, but there's a global cost Malmquist. Is it necessary? Well, maybe not, but it depends on some situations. Then you have the secular global profit Malmquist. In short, profit Malmquist. We will not look at that much because these things are quite voluminous. So, we also have the global frontier shift. I did not teach you the frontier shift, okay? But I will teach, not you, I will teach in my normal lecture slides, okay? Because the frontier shift is an important thing to look at. Now, the frontier shift is normally when you are dealing more with conventional population communication. So when you want to speak more about the overall population instead of talking about individual observations, so you look at it from the frontier. You can also use this frontier shift to look at differences in groups. So you can look at foreign banks and domestic banks. Which one of them are doing well? Okay, and I'm talking about the average best performing foreign banks versus the average best performing domestic banks. You can look at banks that are universal and banks that are, investment. Okay, and you can even extend it to 3 or more groups. And then what we are going to look at today, Biennial Malmquist. The Biennial Malmquist. It's been extended slightly to negative data. It has also been slightly extended to meta-frontier cost Malmquist. It's been slightly weakly been written in Biennial cost Malmquist. And that's why I put a question there, because it's not explicitly clear. But there is a meta-frontier cost Malmquist. Dinah will know about that. But we don't have anything called biennial meta-frontier cost Malmquist. There's nothing there for that. So as part of your development thesis, you can look at that. Or if you want to look at that, let me know. There is overall Malmquist by Afsharian and Ann. So there are different kinds of these Malmquists. Sometimes some of them are just useful for what you're going to use them for. Ladies and gentlemen, we're going to look at just the Biennial Malmquist by Pastor and Lovell. And I want you to really pay attention. Okay. We'll be looking at this from slides 1 to 25. We'll pause and take a break, and then we'll wrap it up with the rest. The slides 1 to 25 is just the theory, and then we'll pause and then come and do practical lessons using softwares, R and MaxDA. The BMI, the Biennial Malmquist Index, was introduced by Pastor Asmmild and Lovell. Who knows Asmmild? Who can tell me something about Asmmild? Anybody?
Doc, I think you have a paper with you.
Yes. And she happened to be my supervisor, my PhD supervisor. I really, really admire her and the way she was able to baptize me in the sea of good efficiency and productivity analysis. Anyway, the good thing about the Malmquist Index, the Biennial Malmquist Index, are three. But there's a disadvantage of it. It's not transitive. What does it mean? What do we mean when we say it's not transitive? Anybody has an idea? When we say an index is not transitive. Do you remember something related to indifference curve? When we talk about indifference curve are everywhere dense. Indifference curve, transitivity, assumption, and those things. Okay. We used to talk about things that if A is bigger than B and B is bigger than C, then what? If A is B and B is preferred to C,
A is bigger than C.
It has to do with something related to that. To be honest, it had to be with that. Okay. So that is one thing that is one of the properties of index numbers. Okay. But it's wonderful. The Biennial Malmquist Index is wonderful. Why? Because it avoids linear programming infeasibilities that you will experience under the VRS. When we were estimating the Malmquist Index, do you remember I mentioned about infeasibilities? Did I? Did I talk about linear programming infeasibility? No, no problem. But do you all remember that in a normal linear programming, there is something called infeasible solution? Do you remember?
Yes, though.
Yes. Infeasible solution. Dinah, you should remember this the most.
Yes, though.
We used to say that when the primal model is infeasible, then the dual is what? Unbounded.
Unbounded.
Yeah. When the primal linear programming model is infeasible, then the dual is unbounded. Now, infeasible means that there is no solution. There is no solution. Okay. It's more or less outside the solution element. And to be honest, we are going to demonstrate the infeasibility clearly with a simple graph. And then we will see how it is a problem in productivity studies. And then we correct it with a biennial Malmquist treatment. So it avoids that. The other thing is that it also allows you to compute technical change. First of all, productivity is decomposed into efficiency change, which we call the catching up to the frontier. And then the other one, which is the technological change or the technical change. And that one is called a frontier shift. Now, the Biennial Malmquist allows for that. And this is in comparison with the sequential Malmquist. Okay. Even though the sequential Malmquist may be transitive, okay, it is suffering from technical change situation. The other advantage is that it does not need to be calculated again when a new time period is added to the data set. For example, if you look at the global Malmquist of Pastor and Lovell, anytime, let's say you have some firms that are in year, the other Malmquist indices. So It doesn't have to be recomputed. So let's say you have a sample year of 15, and then you have 2000 to 2009. And the moment you enter 2010, you collected 2010 data and you added it. You added it to your data set, and then you recalculated the Malmquist index for each observation or each DMU. The result will change. Of course, the results will change. Okay. When it comes to the global Malmquist index. But you don't need to recompute the entire data set, the entire Malmquist, when a new time period is added to the data set when it comes to the biennial. Because when the new time period is added, it is still going to be with reference to the biennial index. Okay, it is still going to be in relation to the biennial index, and so that is why it does it. We will look at a piece of this when we are going through. So the biennial Malmquist, you create a biennial frontier because there is a biennial technology, and this biennial technology or frontier is defined as a convex combination of observations of the two adjacent time periods that you are looking at. Like I said, we'll be looking at more examples of this. Okay, so let's look at some few details. When you have panel data made up of two time periods, the biennial technology, and I want you guys to know the difference between frontier and technology. If you can remember, I said the other time that a frontier looks at the line at the edge. The technology is both the line plus the space. Do you remember? Okay. The biennial technology is made up of the line, the boundary of the space plus the space itself. And that technology is similar to the pooled meta frontier technology. And this same pooled meta frontier technology is what is used to calculate the global Malmquist index. In a general case, when you have more than two time periods, okay, where the time period is U, you now get a series of U-1 overlapping biennial technologies for each pairwise. This is better understood when we go through the specific examples. All right. And because you have the word biennial, we are talking about two time periods at a time. But we can also have a construction of a triennial Malmquist if you want to do that, where you are looking at 3 time periods at a time. So Pastor, Asmmild and Lovell, they created this. We are going to look at the biennial Malmquist in an output-oriented. They actually did it in an output-oriented distance functions. Okay. But we'll be looking at it more using output-oriented technical efficiency. That's how we'll be looking at it. Okay. We'll be looking at it more with output-oriented technical efficiency, because you know that the distance function is a reciprocal of the technical efficiency and vice versa. We know this technology set and how to create the constant returns technology set. That's the C here. So we'll be using C a lot to represent constant returns technology. We'll be using V to represent variable return. Ladies and gentlemen, in front of you is a biennial Malmquist index. You have biennial Malmquist index for constant returns. That's why you have C, C, and C. And then you have the same thing, biennial Malmquist index under variable returns to scale, which is V, V, V. Now the phi is the output-oriented efficiency score. And since we are using a biennial CRS technology for this, for the top one, the top mathematical equation, it will include both the period T and period T plus 1. Please note something. The biennial is a kind of one frontier that captures, that envelopes the two frontiers. The frontier for t and the frontier for t plus 1. And so when we say biennial is kind of taking the edges of these two frontiers and then creating a new frontier for it. We'll look at an example. And since that is the case, we don't need to go to any geometric mean, because we tend to use a geometric mean when we were dealing with the original standard Malmquist, because the technologies were different. But the biennial, it more or less envelopes the two different T and T plus 1 technologies. So we now have a kind of a one technology, and so we don't need geomeans when defining the productivity index. And so the only difference between the biennial Malmquist for constant returns and biennial Malmquist for variable returns is the letter V, the subscript V that you see there. So please note that the biennial Malmquist, and now guys, I want you to pay attention at this stage. The biennial Malmquist for constant returns is not a big deal. And you come to see, it is the biennial Malmquist for the variable returns which is a big deal. You will come to even learn that the constant returns one, it will coincide with the normal standard Malmquist constant returns. The frontier will be the same thing. It will just take the frontier that is on the extreme section of the observations. But the reason why the one for the VRS is important is because the frontiers can intersect. And one frontier can be way behind the other. So because they can intersect, they can create a kind of a gap in between them. And I'll give you a quick example just for you to appreciate what we are talking about. Let's just take something like this. Okay. Let's just take something like what I'm about to draw here. Now look at this graph that I'm going to just draw here. You have this X and then Y graph. And when we do constant returns, you know constant returns is always going like this. Let's call this T. And then variable returns is another graph. Let's go like that, which calls it T plus 1. Guys, do you see it?
Yes,
Yes,
sir.
sir.
All right. Now pay attention, I beg you. Now, this is constant returns graph, CRS. And if we were to create the biennial Malmquist, the biennial Malmquist will take the one that is on the extreme, which will envelope both the T plus 1 and then the T. Now the one that is on the extreme is the same T plus 1. It's that same T plus 1. Okay. So it will coincide with that. That is why we say that that one is not a big deal, because we already have that frontier. But let's look at a VRS frontier. Okay. I'm going to just clear this, and then we'll look at a VRS frontier. This is a VRS frontier. You have X and you have Y. Now, this is one VRS frontier. Watch how it goes. It goes this way, it goes that way, it goes this way, and finally it goes that way. This frontier is like T, frontier T. Now, let's get another frontier. It starts from here, it goes from there, and then it goes from here. This is frontier T plus 1. So when you're looking at the extremes of the frontier, let me use a different color to explain. When you're looking at the extremes of the frontier, one extreme of the frontier is this section here. Another extreme of the frontier, okay, is this section there. It takes this section, the outer gap, and then it now turns and looks at this, and then it turns and looks at that. So you can see that if you look at this section, this red section, there's a kind of a space, and I'm going to shade that space. There's a kind of a space here, which was not captured So if a certain DMU is in this shaded space, what will happen is that it will not be captured by both the T frontier and the T+1 frontier. Are you guys with me?
Yes, Doc.
If a DMU is here, it will be captured. If a DMU is here, it will be captured depending on the orientation you are using. If a DMU is there, it will be captured. If it's there, it will be captured. But if it is here, up here, and you are trying to look at the output orientation, you have to go up. There is no frontier it will hit. But with the presence of a new blue frontier here, the biennial frontier created, which is a kind of envelopment of the two frontier, the edges of the two frontier. Now, when you're tracing this DMU, which is in the red section, upward, it will hit a boundary. It will hit a frontier. It will hit a biennial frontier. And so, the biennial frontier now helps that guy, which would have been infeasible, to now be what? Feasible. Please, you get a fair idea what I'm just done. I'll show you practically though. Do you get it?
Yes, yes, Doc.
So keep that in mind whilst we proceed. Okay, keep that in mind. So that's what exactly we are saying, that there's a VRS biennial and then there is a CRS, and I've just shown you the VRS biennial is the blue one I created. The CRS biennial is also there, just that it happened to coincide with the T+1 frontier. Now, which of them do you deal with? Well, what even has led to this whole biennial frontier? What motivated it? Well, there have been a lot of arguments in the literature that the Malmquist, the normal standard Malmquist productivity index, is only reasonable when you estimate it relative to the CRS frontier. And all these authors have said that. Greffel, Taji, Lovell, they wrote 1995 papers, which was top. And even, Greffel, Taji, 1997, in American Economic Review, wrote a paper with his colleagues that actually indicated that the Fair, Groskopf, Norris, and Zahn, the 1994 paper, okay, which was an extension. Remember that one was looking at efficiency change, technical change, skill, efficiency change. It was looking at 3 components. Okay. Now, the F, G, and Z extended the 2-factor decomposition to a 3-factor decomposition, which we have learned, which captures skill. This Greffel, Taji guys and his colleagues indicated that there is a problem, a slight problem with that, because it doesn't fully capture the scale element. So they created a new one. And then they went ahead to say that when you estimate the Malmquist under the VRS, it's not kind of sensible, because the true technology best that explains the Malmquist is the CRS. Now, why is that so? They demonstrated that the theoretical Malmquist provides bad measure of productivity in the presence of VRS. Because in the presence of calculating the cross-period efficiencies, we can fall into cross-period linear programming infeasibilities. And I'll show you this practically for you to see the problem. That is only when you estimate it under VRS. But when you estimate it under CRS, there's no problem like that. So which one should you go for? They suggested that go for what? CRS. But isn't it funny, guys, that we have come to learn from the non-parametric statistics, non-parametric test of returns to scale, Semi and Wilson, 2002. We have come to learn that you need to know the true technology under which your firms are operating. Is that not what we said?
Yes, Doc.
Yes, Doc.
So if we have said that, and you have done your statistical testing, and it says that the returns to scale underlying the technology is VRS, then you go and say that Greffel and Taji are saying that the best way to calculate the Malmquist is CRS. So even though your technology is exhibiting VRS, you will not use VRS, but you will use CRS. You get a point? Then why did you even do the test? That is where the biennial Malmquist becomes important, because the biennial Malmquist now helps you to be able to beautifully estimate. Now, why is it not sensible to use the VRS? Griffith, Terji, and Co. said because they produce infeasibilities when you're calculating the mixed period linear programming scores. What if you can solve that infeasibility problem? What if we can still calculate the VRS and be able to handle the LP infeasibilities? The Biennial Malmquist will do that. He will do that, and that is the essence of what we are looking at. So this is a Biennial Malmquist technology. This is a VRS technology, as we know, always in normal linear programming. And anytime I use the T, I use a C, different from the V. You should know that the C is referring to constant returns. The V is referring to variable returns. So let's look at the Biennial Malmquist. This is just a quick rundown. For both the constant returns and the variable returns, these are the way you calculate them. Please know that the Biennial Malmquist is defined as efficiency change times the technical change. In both cases, efficiency change times technical change. But remember that you are estimating it relative to the biennial. That is why they are all raised to the power B, because we are estimating it in relation to a new frontier. Now, the efficiency change is defined as what you see on your screen. Okay, theta V, just to indicate that we are talking about efficiency change under variable returns. And then, phi V, and then phi V. So phi VT and then phi VT plus 1. And all of them are, having their DMUs in their respective time periods. That's it there. So let's decompose the Biennial Malmquist. And the first decomposition was the efficiency change relative to the Biennial Malmquist, VRS. Like I said, we are not interested in the CRS. I'll be talking more about the VRS. So you see more of the V. Okay. Now the technical change is given by this formula. Okay. And this formula, don't be confused much about it. This formula you are seeing there is just a cross multiplication. Okay. It's just a cross multiplication of what you see. So it's just like dividing both sides of this bullet 2 here by ECV. Divide right side by ECV, left side by ECV, and that will give you the technical change part. In reality, it's given by what you see here. Everything is V, 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 V. Everything is V, V, V. This is a technical change. Now, how is this technical change different from the original standard technical change, the Fair-Groskopf, Norris and Zahn, or the Fair-Groskopf, Langren and Roos, 92.1 and then 94.1? How is it different? Well, you can see that there is no to the power half. Do you remember that one was to the power half or square root of that? So here there is no square root. And why is there no square root? Because it is in relation to the biennial frontier. But watch carefully, watch very carefully. When you look at the last equation, you will see that some portion of it is to the biennial frontier, the technical change part. Some portion is to the biennial frontier. You can see phi VB and then phi VB. But another section is phi V T plus 1 and then its diagonal is phi VT. Do you see what I mean?
Yes.
So the technical change part, has got the biennial frontier being measured in relation to, okay, and then plus the other frontiers are also being used. Okay, and we'll see that, we'll find out exactly why that is so. So this technical change, which is called the biennial technical change, it maintains all the own period efficiency scores of the efficiency change in the normal Malmquist. So if you look at the own period efficiency scores, watch it here. You see that one is all maintained. Look at it. It's all maintained. The problem is not that, because in the efficiency change, we don't have cross period problem. Do we have? No. Because we are not estimating anything related to a cross period frontier. And that's why you wouldn't have a problem of infeasibility there. But in the cross period, that's a sentence here, okay? But the cross period scores are rather computed relative to a biennial frontier because they are the ones that bring out the infeasibility. And the second thing is that since the biennial frontier combines both periods 1 and 2, there is no need for a geometric mean in defining the biennial technical change, which is what I said, there's no to the power half there. Let's look at the 3-factor decomposition. You remember I indicated that there's a 3-factor decomposition? Well, that's where you bring the scale efficiency change. The scale efficiency change is defined finally as the last term here. Watch it carefully, and you see that that one, it has both the biennial in all of them to the power b, in all of them to the power b, but the subscript one, some of them are constant returns, some of them are variable returns. Okay, some of them are constant, some of them are variable, and that is because we are dealing with scale. And anytime you are bringing scale into the picture, you should know that we are bringing both CRS and VRS, because the gap between CRS and VRS always represent the scale. And VRS says that size matters. CRS says size does not matter. Okay, and the scale efficiency change throws more light on that. And that is why you can see that that one, all of them are measured relative to the biennial constant or biennial variable constant, variable return scale. So if you bring about the scale element, then it means that the biennial Malmquist can be redefined as EC vein B to the power B times technical change VRS to the power B. And these two, which are bracketed, is what is equal to the normal Malmquist under VRS. And also the scale efficiency change under the VRS, under the biennial, you can see that it doesn't change in both of them. Okay, this is like pure technical efficiency is equal to technical efficiency is equal to pure technical times scale. That is a principle being demonstrated here. Okay, a typical example will do the work. So when we should bring all of them into the picture, if you look at this last portion there, when we now bring everything into the formula, this becomes finally the Malmquist, biennial Malmquist productivity index. Okay, constant returns. And now the reason why we have brought C there is that inside the element you get a V. So the first part, this EC times TC, this makes the biennial Malmquist in variable terms. Okay. And watch the thing. Even though you have the curly bracket, you still do not have to the power half. In terms of distance functions, this is how we would have expressed them. In terms of, and go check it later, you see that everything at the bottom is equal to what is at the top. So because of the reciprocal element between distance function and efficiency scores, anything at the numerator is swapped with anything at the denominator in the second definition under distance functions. Just for example, if you look at the distance function, you have t plus 1, t plus 1, t plus 1. That is what is in the bottom of the efficiency score. So you have t plus 1, t plus 1, t plus 1. So that is it. You can look at the rest for yourself. Wouldn't you like to have an example? I think that would do, right?
Yes, that will.
Okay, so this is an example. I wonder, I don't think you've seen this data set before. Normally, you generate your own hypothetical data set. You will illustrate it just like the way I'm going to do. There are 5 firms in years periods 1 and periods 2. So if you look at the first firm A in period 1, the input was 4, the output is 5. Now you can see that I'm using input-output graph, not input or output, because the biennial Malmquist can best be explained using CRS and VRS frontiers. And the input graph, the isoquant graphs, and the output graphs, the concavity graph. These graphs, they don't really show constant returns and variable returns better. They don't really show. It's difficult to really show that. And so that is why we are showing it in the input-output graph. So DMU E has got 6 inputs for X, 6 inputs and then 9 outputs. Let's scatter plot this and let's generate the frontier for year 1. So this is a scatter plot and this is a frontier for year 1. As an example, look at DMU A1. That's DMU A in year 1. You can see that, look at the values. It was 4 of the input, Y of the output. The input is on the X-axis. So 4 on the input, that is this horizontal line. And then 5 of the output, you can see that it's right in the middle of these 2 lines. I've deliberately added grid lines so that it will showcase and helpful when you are estimating the rate. So this green frontier is the VRS frontier for year 1. Now, how do you calculate the efficiency score of every firm relative to this VRS frontier? Remember the definition, and you are going to calculate it. This is a definition. That output oriented, so we are going output oriented way. It is always the distance from the origin to the frontier. Remember, this is efficiency. It's not distance function that we used before. And then this is divided by the distance from the origin to the frontier. Distance from the origin to the frontier. Okay, so how do you calculate that for DMU A1? Who can guess? Something over something. Who can tell me? You can guess and tell me. Distance to the frontier divided by distance to the firm. Chris.
Doc, this will be 4/4. So you get the value of 1.
Check the values well. Check the Y values you mentioned.
Sorry, the Y value. So it would become 5/5. Yes, it would be 5/5 instead.
Let me just go and show you the variables. These are the variables. 4 and 5. So keep that in mind when you're talking now.
So, Doc, please, I'm using the output values, the Y values. So that would be
output. It's not from the origin. When you are picking from the origin, you don't pick from the origin here now. You pick from the axis.
From the axis.
Did I define it as origin? Okay, maybe that's my definition. But when I define it as origin like this, it's not moving towards the thing. It is upward to the top or rightward to the horizontal right. So you're
saying that
distance to the frontier, which is in the output section, is 5, isn't it? Divided by what? 5.
Divided, yes, please.
Does it make sense?
Yes, please.
It's 5/5. Do you all agree?
Yes, Doc.
Yes, sir.
So please remember, it's a distance from here to the frontier, and you read it there, 5. And then the distance from here to the firm, it just happens to be that that firm is also at the same frontier, so that is also 5. So that makes it 5/5. What will be the output-oriented efficiency score? Okay, output-oriented means you go the vertical section, Y line. For E1 will be what? E1 score will be what? What over what? Chris?
It would also be 9/9.
9/9. What about D?
Yes, please.
Chris?
But D would be 14/14.
Exactly. Now let me trick you small. What about C? C1?
C would be 7/14.
Okay. Do you guys all agree? So these are the. Did you say 7/14 or 14/7?
I said 7/14.
It should be the other way around. Remember, it is distance to the frontier.
Sorry, to the frontier. Sorry, to the frontier. So 14.
14/7.
14/7. Sorry.
Okay. Then what about B?
So B would also be 14/12.
Exactly. Now the rest of you have to learn how to do these things. You've learned it before. So this gives you the score for each of them. These are own periods, so there will not be cross-period problems. This is a final answer. I'm sure you can do that. Okay. Now let's go to the next one. Now let's go to year 2 frontier. This is year 2 frontier. We've labeled it as red. Look at the data carefully. They are the ones at the bottom in the white screen section. So A is now having 8 inputs and then 6 outputs. Now, what would be the output-oriented technical efficiency score for A2? Who can tell me what divided by what on average? What divided by what on average? Daniel Ameibo, what would that be?
For A2 to be 9 divided by 6.
9 divided by 6, something like that. What about B2? Let's go to next person, Derek Awua, B2.
B2 will be 6 over 6.
6 over 6. Edwin, C2.
C2 will be 9 over 2.
If you look at C2, yes, around that situation, even though not exactly, at least the idea is there. Let's go to D2, and that is for Alec Blame.
And please, 10 over 10.
And then finally, Emmanuel Edu, E2. Emmanuel.
Doc, please, 9 over 9.
Okay. So those answers that you guys have given are fine if you have the real values. If you look at, use your eye alone to do it, you won't get the real value. So what I do is I normally let the software do for me, and then I will do the division sign and know the actual value. So this becomes the own period efficiency score. They are also own period. Okay. 6 over 6. Somebody mentioned 6, 7, but you see the actual value is 6.7. Okay. Now, so this is a green frontier and this is a red frontier. Now let's combine them and we have this beautiful frontier. Now we can calculate the mixed period efficiency scores using the frontiers. I'm sure by now you all know how to calculate mixed period. The same approach, but just that when you are calculating A1, it is in relation. A1 is a green line. It is in relation to the red line, frontier 2. A1 is in year 1 and relative to frontier 2. So what will be the cross period efficiency score for A1, output oriented? I'm going to continue calling you cross period. Okay, Chris.
Sorry, it would be, it looks like 7 point something, about 7.5 over 5.
Perfect. You have a fair idea about it. Okay. It is that gap that you are seeing here. That little gap there. Good. Good. What about B1? B1. Savior. What about B1?
No, that would be 14 over 12.
14 over?
12.
Are you sure? Yes. 14 over 12. B1. No, that's wrong. Because B1 is in year 1.
Hello, Doc. I think it's wrong.
It's
I know it's wrong.
12.
I've already said it's wrong. So if you know, raise your hand. That's how we work it. Okay. The moment the person is wrong, you raise your hand. You see, now that I'm asking you questions, when it's wrong, you raise your hand and then you address it. Yes, Daniel, tell us the correct answer.
The correct answer is 10 divided by 14. By 12. 10 divided by 12.
You see how we're all quiet listening to you. So 10 by 12. Let's go to C1. C1. Who will get that for us? Yes, Yao. Yao.
Dog, it will be 10 divided by 7.
10 divided by 7. Very good. You guys are calculating cross period very nicely. So let's go and see all the results for those. Okay. Let's go and see all the results. Of course, output-oriented efficiency score is always 1 and above. If it is 1, it's efficient. If it's above 1, it's inefficient. So all those that are below 1 for output-oriented, they are super efficient. They are all super efficient. And that's what you guys can see there. Okay. So how many super efficient firms do we have? Now, this one did not produce any infeasibility. We were able to get a score for every one of them. So no problem. So now let's go to cross-period efficiency for the other ones, A2. So let's look at A2. Who will do A2 for us? Thelma, A2.
A2 will be 11 point something over 6.
11 point something over 6. Very good. B2. B2. This one, who can raise a hand? B2. B2. Yes, Xavier.
No, that's 6 over 6.
Sorry?
6 over 6.
Again.
6 over 6.
No, that's not correct. B2. Remember, B2 is in year 2, and you are measuring it relative to the green frontier. Green frontier is in year red, and you are measuring it relative to the green frontier. Thelma.
It will be 5 point something over 6.
No. Viscount.
Dog. Hello, dog.
Go ahead. I've called you. Answer it for us.
That is 5 over 4.
Okay. Thank you. That's wrong. Who will get it? Chris?
Please, I think it's about 4.2 divided by 2.
No. Okay, so let me tell you why you are all struggling. If you look at B2 on the graph carefully, you will notice that you are relative. B2 is in year red, is in year 2, and you are measuring it relative to the green frontier, vertical. And there is no green frontier vertical. Is there any green frontier you see below above B2 directly? No. And so, because there is no green frontier, you cannot assess this cross-period efficiency. It is one of the infeasible DMUs in cross-period language. This is the problem we get if we are using the standard Malmquist Productivity Index. B2 cannot be obtained. The cross-period efficiency scores, the mixed period efficiency score, the intertemporal efficiency scores for B2 can never be estimated using the standard technical Malmquist approach. Because there is no frontier for year 1 that B2 can be measured relative to. Do you guys see that now?
Yes, please.
Yes,
Exactly. Now let's go to C2. C2. Output-oriented efficiency score of C2 relative to frontier 1. Nathaniel.
that's also infeasible.
Exactly. That is also infeasible because there is no green frontier above it or below it. It is on the side of it, but we are not doing input orientation there. We are doing output orientation here. And so in an output directional movement, there is no cross-period frontier for it. So C2 is infeasible. Now let's go to D2. D2. Nathaniel.
D2 will be 13 over 10.
Exactly. It will be 30. You see that one, there is a green frontier above D2. And because there's a green frontier above it, we can estimate the cross-period efficiency for it. Now let's go to E2. E2. What will be the cross-period efficiency score for E2? Tarish.
Doc, please, that would be 9 over 9.
Exactly. 9 over 9 because it's happy to be at the same point as E1. So now you can see that if we are to go by the standard Malmquist approach, the scores that are going to happen are what we are going to show. Okay. Look at the scores. Where is that? So these are the scores, cross period. You can see that B2 and C2 are not feasible. You cannot get a score. And we know that we know the value, but we don't know the frontier point. And so question mark is infeasible. So what is going to happen when we are estimating the Malmquist as far as these two guys are concerned? Do you think we'll be able to get a Malmquist index for them? Well, once you don't have a feasible solution, we can't calculate the Malmquist values for these guys. Now that's a problem, but we'll come to solve that. So note the point there that the infeasibility only occurs under the VRS, not the CRS. And the graph we are using is VRS. Who can tell me why? Why we will never get infeasibility under the CRS? Look at the graphs and it will help you. If we were to, yes, Chris.
Doc, please, it wouldn't occur under CRS because under CRS the graphs would never intersect.
Exactly.
So because they never intersect, there won't be any form of infeasibility.
Exactly. And even if they do intersect, like E1, it will only all be at 1, 1, 1, 1, 1. Isn't it? We'll get it at the same value. 1, 1, 1.
Yes, please.
So there will be no need. Okay. So they will not cross over. They will not intersect. Very good answer. If I were to draw a CRS line for this, it will pass through B2 from the origin. It will pass through V2 going up, up, up. And then for the frontier one, it will pass through A1 going up, 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 up from the origin. And they will never intersect. Perfect answer. Now, let's move on. So how do you handle it? Anyway, this is the final result. If you have to substitute the scores now into the, as for the efficiency change, you get the answer for it. Because we estimate that one in relation to your own frontier, no cross-period analysis. But with the technical change, we cannot get the scores. And as long as we cannot get a technical change, we will not be able to know the actual Malmquist productivity index for B and C. So in the end, do you know what some people do? They drop these DMUs. They drop B, they drop C. What if you have 100 DMUs and 80 of them have this cross-period efficiency problem? What is going to happen, Dinah? What's going to happen? If you have 100 DMUs, okay, and you are going to drop the rest. Chris, what's going to happen?
What would happen is the results you get within the fair representation of the industry.
Perfect. The score will not fairly represent the industry. So if you say that the industrial average is 0.86, 0.9, you see I've put 0.94 there. I don't even know how I got a 0.94 there. At the bottom, I've put 0.81 for the Malmquist. I don't even know why I got a 0.81. You can't make a fair, information will be lost. Especially if you are getting more of these infeasibilities coming in. And that is a problem of the standard Malmquist index. Okay. This is a good thing. So first problem, let's dig into the problem and wrap up there. And we'll have some short break. First issue with the above Malmquist index is that the linear programming infeasibilities under VRS mixed period scores make it very hard to get a Malmquist for some of the firms. You can see that. Okay. The other clear thing is that such infeasibilities did not allow for the calculation of the technical change because it relies on the cross-period efficiency scores. And so overall information may be lost through infeasibility. I use the word may because if those infeasible firms are few, then information loss may not be that much. If they are not few and they are many, the information loss may be great. That is how this is you see, I deliberately, let me show you something. I deliberately drew a graph to pinpoint the infeasibility problem. Okay. So when you are drawing the graph, I deliberately put some C2, some DMUs here, like C2 and B2. I could have put another DMU, looking at the graph, I could have put another DMU F1, F2 here. And so once you have F1 and F2 dropped here, okay, for 6 on the y-axis and X on the x-axis, and 3 on the x-axis, okay, then you could have generated more infeasible firms. And once you generate more infeasible, so when you have drawn your graph, you can know where to put the thing. So you can see that for those firms that are here, they will have a problem of getting a green. But watch something. If you go and put it at this point here, okay, let me just shake you small. Okay, if you go and put it at a point here, you will have a problem. Okay, where I've just identified here, you will have the same infeasible problem. But the moment you shift it past this line, the moment you put a DMU here, you will not have that infeasible problem. So it's a location, this location, any location here, any location there, that is where the infeasibility is. Are you guys with me?
Yes, please.
Yes, Doc.
For the output oriented case, if we were doing input orientation, the problem will not happen here. It will rather happen at this section. Okay, it will rather happen at these sections. Okay, because when you are estimating the efficiency of a firm here, okay, relative to a frontier, it will happen somewhere at this section. If we're doing it in the input oriented section. But that's a way to demonstrate a problem. Now that you've demonstrated a problem, you can now be able to think through on how to solve the problem. Infeasibility is a big issue. And we'll come back to look at that by now bringing the biennial Malmquist into the picture.